Let's now move on to an example. So we have a study that was conducted to determine the effects of sleep deprivation on subjects' ability to solve simple problems. The amount of sleep deprivation varied over 8, 12, 16, 20, and 24 hours without sleep. A total of 10 subjects participated in the study, 2 at each sleep deprivation level. After his or her specified sleep deprivation period, each subject was administered a set of simple addition problems, and the number of errors was recorded. The results shown in the following table were obtained. So we have a table with the number of hours sleep, which is X, and then the number of errors that they make on the simple addition test, which is Y. Now, given that information in the table, we can compute some summary statistics like X bar, Y bar, S sub XX, S sub YY, and S sub XY. We're going to use this information to construct our linear model. So the first thing we want to do is find the regression line for estimating the number of errors from the number of hours without sleep. So in order to do that, we're going to have to compute the slope, beta sub 1 hat, which is S sub xy over S sub xx. We have that is 152 over 320, which gives us a slope of 0.475. Then beta sub 0 hat is y bar minus beta 1 hat x bar, and that's going to be 10.6 minus our slope, 0.475, times x bar, which is 16. And if we work that out, we're going to get 3. Okay, so what is our regression line? Y hat is beta 0 hat plus beta 1 hat x. And that's going to work out to 3 plus 0.475x. Now we want to interpret each one of these parameters. So beta 0 hat, okay, that's somebody who's going to have 0 hours of sleep deprivation. Okay, so essentially a person who just woke up, we're thinking about that as 0 hours of sleep deprivation, is estimated to make 3 errors. That's the intercept. Now beta 1 hat, which estimates the slope, okay, we're going to say that we can interpret that saying for each additional hour without sleep, we're going to estimate the number of errors will increase by 0.475. Okay, now that we have our regression and we understand what each of the parameters means, we want to understand, does the data present sufficient evidence to indicate that the number of errors is linearly related to the number of hours without sleep? So what we want to do is, if there's a linear relationship, or if there's not a linear relationship, then the slope essentially is 0. So when the slope is 0, we're thinking that's not linearly related. But if the slope of our regression line is not 0, then we say that the two quantities are linearly related. Let's just take a second to understand what that means. What I'm saying is that if the slope is 0, then y is equal to beta 0 plus 0 plus epsilon. So essentially it's equal to a constant plus the error. And in that case, there's no linear relationship. So if beta 1 is not 0, then we have the linear relationship. So I want to write down what the rejection region is going to be for this problem. The rejection region, when we compute it for our t statistic, is we want the t to be bigger than t.025 with 8 degrees of freedom. We would have to look that up on our chart. What is t.025 with 8 degrees of freedom? So I'm going to bring up the chart here. Okay, we're going to go to the t.025 column with 8 degrees of freedom. That's going to give us 2.306. So our rejection region is that absolute value of t is bigger than 2.306. Okay. Now, what we're going to need is an estimate of our standard, or our variance, so our sample variance. And recall from last time, our sample variance is the sum of the squares of the error divided by n minus 2. So we will remember that the sum of the squares of the error we can calculate as s sub y minus beta 1 hat s sub xy. And we're going to divide that again by n minus 2. And if we plug in our numbers, we have that that's 112.4 minus 0.475 times 152. And then we're going to divide that by n minus 2, which is 10 minus 2. If we work that out, our sample variance is 5.025. Okay, so now I want to find the t statistic for beta 1 hat. So that's going to be beta 1 hat. We're going to compare it to 0. And then we want to divide that by square root of C11 times S. In that case, that's going to be beta 1 hat minus 0 divided by the square root of C11 is 1 over S sub XX. And then we're going to multiply that by S. So that's 0.475. We're going to divide that by the square root of 1 over 320, because that's S sub XX. And then S is the square root of 5.025. So our t statistic in this case actually is 3.791, and that's going to be for a degrees of freedom of 10 minus 2, which is equal to 8. So now we're going to ask ourselves, well, what is the p-value based on a t statistic of 3.791? So I'm going to go back to my t chart and look at 8 degrees of freedom. And I'm going to find 3.791. I'm going to notice that it lands right there between these two columns. And so my p-value I can bracket as being 0.0005 is less than p over 2, which is less than 0.005. That tells me that p is actually between 0.001 and 0.01. So if we're given a particular alpha value, say 0.05, we can reject the null hypothesis. Okay, what does that mean? That means that there is sufficient evidence to conclude that the number of errors is linearly related to the number of hours without sleep. Okay. Now, I would like to find a confidence interval for the slope. So we're going to move on to finding a confidence interval for the slope. The formula for the confidence interval is going to be beta 1 hat plus or minus t sub alpha over 2 times the square root of C11 times S. That's going to work out to 0.475 plus or minus t sub alpha over 2 we saw was 2.306. And then that is going to be the square root of 5.025. That's the S. And then we're going to divide that by the C11, which is 320. This part, if you work it out, is 0.289. That's going to tell us that our slope, or our confidence interval for the slope, if we find a 95% confidence interval, is 0.186 to 0.764. Okay, so what does that mean? It means that we are 95% confident that an increase in 1 hour without sleep will produce between 0.186 and 0.764 additional errors on average.